We're going to cover section 1.5, reviewing properties of exponents. So with a power, we have kind of different parts of the power. We have the exponent, which is the little number telling us how many times to multiply the base together, and the base is the large number. Now, the base can be comprised of more than one factor. Reading this one out loud, this can be said -2 times x cubed, or x to the third. So that exponent of 3 is only being applied to the x, not to the -2. So the x is the base of that power, not the -2. So in expanded form, -2 times x cubed, if we expand the x cubed, that means x times itself 3 times. Okay? If we want to include more than one factor in the base, we need to use parentheses, like in the second example. So now this exponent of 3 is being applied to both the 2 and the x. And this is kind of like a -1 being multiplied by that. So my base here is 2x. And then in expanded form, the negative I'm just going to write as -1. Then the 2x is being multiplied by itself 3 times. So that's what changing the base does, is now we're multiplying 2x times itself 3 times instead of just the x. Now in this last one, all of it is the base, everything in parentheses. So this is -2x times itself 3 times. So I'm going to get a different answer for all three of those, which is why it's important to recognize which part of the expression is the base. Okay, now let's take a look at some other rules here, you guys. So if we look at exponents, my base here is 2, and as I change the exponents, let's start with 2 to the first. 2 to the first is 2, 2 squared is 4, 2 to the third is 8, 2 to the fourth is 16, 2 to the fifth 32. So as I work my way up, increasing my exponent by 1, whatever my base is, that's what I'm multiplying by. So I'm multiplying by 2 every single time. So if I go down and decrease my exponents by 1, I'm dividing by 2 each time. So if I follow that pattern, 2 divided by 2 is 1. So because exponents involve multiplication and division, we can't divide by 0, right? And when I divide by, something by itself, it has to equal 1. So that's going to keep that pattern of multiplication going. Now, 0 is kind of an interesting case. So 0 times itself 3 times is 0. 0 times itself twice is 0. 0 times itself once is 0. So it could be argued that 0 to the 0 power is also 0. But if we're going to maintain this definition that anything to the 0 power is 1, we're actually going to keep that definition consistent. Okay? I've linked an additional video, you guys, kind of discussing the controversies about 0 to the 0 power. And the first minute or two, if you want to watch that, is pretty interesting, kind of explaining more why we're going to define 0 to the 0 power as 1. Okay, exponent properties. So we're going to keep this property that anything to the 0 power is 1. We're also going to take a look at negative exponents. So anytime I have a negative exponent, what we're going to do is not considered simplified unless the exponents are all positive. So to make it positive, we're going to take the reciprocal of that expression. So this is 2 different ways we can write that. So if it's a fraction raised to a negative exponent, we're just going to flip it, taking the reciprocal, and then raise it to the positive exponent. Okay. Notice these are not the same thing. Okay. And this is not the same thing. So be careful about those distinctions. Okay. All right. So we want to write each of these using a positive exponent. So anything to a negative exponent, we can put a 1 over it, and it becomes 2 to the positive first power, which is just 1/2. Fractions, take the reciprocal, 4/3, and then raise it to the second power. So this means 4/3 times 4/3, which is 16/9. So another way to think about that is we're squaring both pieces of the fraction. 4 to the negative third is 1 over 4 to the third. 4 to the third power is 64. So I get 1 over 64. Okay. All right, couple more exponent rules here, you guys. So we have the product of powers. So here's kind of the generic explanation. If the bases are the same and we're multiplying, we get to add the exponents. So here this would be 9 to the 5th power. And then if I wanted to, I could evaluate what is 9 times 9, 5 times. Here, I want to do things that are alike. So for example, this is multiplication, so I can actually go ahead and just multiply 5 times 3, which is 15. Then I'm going to apply the product of power rule to things that have the same base. So the x's, so x squared and x to the fourth, 2 plus 4 is 6. And then the y's, I have to the third and -1, 3 plus -1 is 2. So that would be my simplified expression applying that product of power rule. Power raised to a power. This here, oh, I'm sorry, I'm skipping one. Quotient of powers. I am always going to do the top exponent minus the bottom exponent, okay? Another way to think about this, you guys, is I'll show it to you in steps. Okay, so here, if I follow this rule, I would become 3 to the 5 minus 2, which is 3 to the third, or 27. Here, if I do 5 minus 7, I get x to the -2, and that's not totally simplified because I don't want to finish with a negative exponent, so it also is going to apply my negative exponent rule. Now, there is actually kind of a shortcut to this, you guys. Instead of having to do this intermediate step, I could also notice that 7 minus 5 is 2, and the bigger exponent is on the denominator, so my answer is going to be in the denominator. So here, 5 minus 2 is 3. This is in the numerator, it's over 1. 7 minus 5 is 2, but the bigger one's in the denominator. So that is kind of a shortcut you can use if you'd like. All right. Power to a power, we multiply the exponents. So here, 2 times 3 is 6. Here I get x to the -12, and again, I don't want to finish with a negative exponent, so my final answer would be 1 over x to the 12th. If I have multiple factors inside parentheses being raised to a power, this is applying the power to every single piece inside. So this is the same as 2 squared and x cubed squared, which then I can apply my rule of multiplying exponents. So then 4x to the 6th would be my simplified expression there. So here I'm going to apply the negative exponent to every piece. So I get 4 to the -2, x to the +6, I'm multiplying those two, and y to the -2. So everything with a negative exponent needs to move down. Positive exponent can stay where it is. And once I move them, the exponents become positive. So then this becomes x to the 6th over 16 y squared. Okay, when we are raising something to an exponent as a fraction, we are applying that outer exponent to every piece inside. So x to the third to the fourth becomes x to the 12th, multiply the exponents. I'm also going to do the same thing with the denominator. So I'm going to get y to the 8th there. Okay, here I'm going to apply that squared to every single thing inside. So we get x to the -4, y to the 6th, z squared. Move that x to the 4th down, so I get y to the 6th over x to the now +4 z squared. Okay, so we want to simplify these expressions as much as we can. This is how we know we've simplified as far as possible. There's no zero exponents, no negative exponents, and each base occurs only one time. So that base part means I can't have multiple x's or multiple y's. We have combined them using our rules. So 1 over 3 squared, or 1/9. Here, I'm going to go ahead and flip and use the reciprocal to get my exponent to be positive. And then that's the same as 3 squared over 2 squared, or 9/4. Okay, -5 to the -5th is 1 over -5 to the 5th. And -5 to the 5th, I don't know that one off the top of my head, you guys. Make sure, notice how I kept that in parentheses. I wanted -5 to the 5th. I want -5 to still be the base. So if I do -5 in parentheses raised to the 5th, get -3,125. So 1 over -3,125. Okay, I'm looking for, this is multiplication, so I'm going to multiply the 3 and -4 and get -12. X to the 7th times x squared, add those exponents. and y squared y to the negative 1. Add those exponents, and I just get y to the first. And we don't usually write to the first power, you guys. We just would write y. Less complicating the expression when we can. Okay, to the third power here, and I'm actually going to zoom in just a hair on these ones, you guys. Those are kind of little. There we go. Okay, so here I have an expression. I want to apply this 3 to every single piece. But what I actually like to do is look in the parentheses and ask myself, can I simplify anything in the parentheses first? So right now I'm noticing I have z's here. Remember, we can subtract the exponents, and the answer is going to go wherever the bigger one is. So 5 minus 3 is 2, so I'm going to get z squared in the bottom when I simplify that. So I haven't taken care of the cubed outside, but now I can. So now this third power is going to apply to everything, so I'm going to get y to the third over z to the sixth. I'm multiplying there because I already had an exponent. Okay, here, this is division or a fraction, so the regular numbers, you want to think about that as just reducing fractions. So here, let's see, I can divide both those by 8. So 48 and 40, I think reducing fractions, if I divide that by 8, I get a 6 on top and a 5 on the bottom. So 48 40ths reduces to 6/5. If I subtract the exponents here, 3 minus negative 1 is a positive 4. Negative 2 minus negative 3 is a positive 1. Okay, so those are going to end up in the top, so that would be my final expression. I can make it look a little nicer, kind of centered over the 5. All right. This guy, another way to think about this is a negative 4. I like to apply the negative to the numerator a little bit simpler. So this, I have negative 4 squared x to the 4th over y to the negative 6th. Okay, so the y to the negative 6 needs to move up to make the exponent positive. Negative 4 squared, negative 4 times negative 4 is 16. And by moving that y to the 6th up, I don't have anything on the denominator besides 1. So I can just write it like that. Okay, there's a few more examples using properties of exponents. Thanks for watching.